Professor Dave and Chegg here. We already know about the types of interactions atoms will participate in to form molecules. These are the intramolecular interactions that hold compounds together. But there are also certain kinds of electrostatic interactions that an entire molecule can make with other molecules. These are called intermolecular forces, and they aren't actual chemical bonds, but they can be fairly strong, and they determine many characteristics of a substance. We definitely need to know about these as they inform our understanding of so many chemical phenomena. So let's define them now.
First, we have ion-ion interactions. Large ionic solids are held together by these networks of ionic bonds, which are the strongest intermolecular force, because they involve formal charges. These are essentially just the ionic bonds we already learned about, simply applied on a larger scale. So let's quickly move on to the next intermolecular force. Next, we have ion-dipole interactions. So first, we must recall what a dipole is. The covalent bonds in a water molecule are polar, because oxygen is more electronegative than hydrogen and will pull the electrons in the bond towards itself. Because of the bent shape of the molecule, when we combine these vectors, we see that water has an overall dipole, or a side of the molecule with some electron excess and a side with electron deficiency. Dipoles can make electrostatic interactions because the partially negative side is attracted to positive charges, and the partially positive side is attracted to negative charges. So when sodium chloride dissolves in water, the sodium ions make ion-dipole interactions with the negative side of water's dipole, and the chloride ions make ion-dipole interactions with the positive side of water's dipole. Each ion can make several of these interactions, which are very energetically favorable, and this is why sodium chloride will dissociate in water in the first place. Next, we have dipole-dipole interactions. As you can guess, this is when dipoles interact with each other, as with pure water. When in liquid form, water molecules will move in such a way so as to always be making electrostatic interactions between the negative end of one dipole and the positive end of another dipole. In this case, these dipole-dipole interactions qualify for a special title, hydrogen bonds. This is when dipoles generated by NH, OH, or FH bonds interact with each other. These are just especially strong dipole-dipole interactions. They are especially strong because these are the most electronegative elements, so they will create the most strongly polarized bonds, resulting in a very strong dipole and therefore very strong dipole-dipole interactions. We can almost think of partial charges as some fraction of a formal charge, so the greater the partial charge, the stronger the interaction, though never quite as strong as interactions between formally charged particles. Lastly, we have London dispersion, often just called dispersion interactions. This is the consolation prize of the intermolecular forces, because any substance can do it. Only ions make ion-ion interactions, and only covalent molecules with a dipole can make dipole-dipole interactions, but absolutely anything can make dispersion interactions. For example, take a look at helium. Helium is a noble gas, and due to a full valence shell, it does not make bonds with other atoms, so a sample of helium is just a bunch of helium atoms. Well, the electron cloud around a helium atom will at any time be slightly skewed in one direction. This will result in something called a momentary dipole. This means one side of the atom is ever so slightly partially negative, and the other side is slightly partially positive. This is dramatically weaker than a formal dipole, but it still exists and can be measured. If this momentary dipole approaches another helium atom, it can generate an induced dipole, meaning the slight partial negativity repels this electron density over to the other side of the atom, so that it will also have a slight dipole, and then there can be a momentary dipole-induced dipole interaction that is described as a dispersion interaction. This is a weak and fleeting attraction, but this is all that monoatomic species and nonpolar covalent compounds can do, and for very large molecules, like some hydrocarbons, the force can become significant. To summarize, ion-ion interactions are the strongest because they involve interactions between formally charged particles. Ion-dipole is next because it involves a formal charge and a partial charge. Then dipole-dipole, which is between two partial charges, and finally dispersion interactions, which happen between tiny induced dipoles.
So when looking at some substance and trying to assess what types of intermolecular forces it can participate in, we just check for a few things. If it bears formal charges, it can participate in ion-ion interactions with other ions, or ion-dipole interactions with dipoles. If it is a polar molecule, which we will need to know its geometry to determine, it can participate in dipole-dipole interactions. Only if there are NH, OH, or FH bonds present can it participate in hydrogen bonds, and literally any chemical substance can participate in dispersion interactions. So that will always be the case no matter what we are looking at. And that covers an introduction to intermolecular forces. Professor Dave for Chegg. See you next time.